Here in section 5.1, we're going to be finding area, and we're going to be using Riemann sums. First of all, this is the letter sigma, and in math, we use it to stand for adding things up, or the sum. So if the things that you're adding up are called like A1, A2, etc., then you could call it AI, as I goes from 1 to whatever, say 5. So this is where you start. It doesn't always start with 1, but 1's a good place to start today. And then this is where you stop. So this symbol right here, or these symbols in black, means take A1, whatever that number is, and A2 and A3, A4 and A5, and add them up. So for example number 1, how about if it is find the sum, and it could be A, it could also be N, as N goes from 1 to 4, and I want you to add up the squares. So this means 1 squared plus 2 squared, 3 squared, and 4 squared. And of course, we could do this without a calculator. That would be 16 and 9 is 25. With 4 more is 29. With 1 more is 30. But what I really wanted to show you is how to do that with the calculator. So I'm trying to get rid of that glare, but it's not working. So if you go right here to list, you go to second list, and then move over to math, and number 5 will be the sum. Then you go to second list, move over to operations, and number 5 will be the sequence. So the sequence part is going to make the actual 1 squared, 2 squared, 3 squared, etc., and then the sum will add them up. So for expression, now if your calculator doesn't look like this right now, you're going to have to type it out yourself, which I'll show you in just a moment. So if you do have this is in your operating system, then you put the expression, which I can just use x as the variable, x squared, as long as right there you tell it x is the variable. And then start with 1 and go to 4. And step means, right here I went from 1 to 2 to 3 to 4, so the step is 1. Now for those people that don't have this part on their calculator, then you would just have some sequence, and then you would need to type it in yourself. So you get the sum by going second list, and then you get the sequence and it puts it on the home screen, and then you put x squared with x going from 1 to 4 in increments of 1. So this is always the start. This is where you stop. And this is the increment, or the step. So in here it's going by steps of 1, 1, 2, 3, 4. And then this is the particular function. Okay, and then it adds them up and says you should get 30. So I got 30. Excellent. Now we're going to be using that to find area under curves. So for example, number 2. Suppose that you have the function 2x plus 1. So that would cross the y-axis at 1, and then it would go up with a slope of 2. And then let's say that you follow it on the x-axis from 0 to 4. And then find this area right here. That is what we're going to use Riemann sums for. So Riemann said, well, this picture right here, that looks pretty complicated. I don't know how to find the area of that. But what I do know how to find is the area of a rectangle. So area of a rectangle is just base times height. So what you do is take this interval and then divide it into pieces. Equally sized pieces. So let's say that I went by 1 each time. So 1, 2, 3, 4. Now the procedure is the same in each one of these, so I'm just going to do it once. I'll do it right here. So you take this as the base of the rectangle, and then you start building the rectangle up and up and up. And then when it hits the rectangle, you know the height. Now you could stop when the left side hits the function, when the rectangle hits the function. You could use the right side, you could use the middle. In fact, we're going to do part A, part B, part C. We're going to do all three of those. So on here, I'm going to stop when it hits the left side. Now, as you can see, that rectangle is a little bit short. It's missing this little part right here. If I were to, on this one, if I were to use the right-hand endpoint, then I would go up, use that as the height of the rectangle, go over, and then that rectangle would actually be a little bit too big. But Riemann sums gives you an estimate for the area in here. And then instead of using 1, 2, 3, 4 rectangles, if we use 8 rectangles, then the little bit that is underestimated or overestimated, it'll be even smaller. Then use 400 rectangles, and each one is going to be very, very skinny. And once you get up here, the error is going to be very, very small. That's where we're going with this. So first of all, you divide this into pieces. So estimate the area. In this case, using 4 rectangles. Part A, use the left endpoints. So that's what I did right here on this rectangle. When the left side hit the function, then I stopped, and then that is going to be the area that we use. Now, when you actually do this, we're going to use the sum sequence. And you don't have to draw a fancy picture, but there are certain parts that you do need to do. One is you need to find this width, which is called delta x. The way that you find delta x is find the length of the whole interval. So 4 minus 0 will be the length of this on the x-axis. So it's going to be 4 minus 0. And then however many rectangles they say to use, you divide by 4. So that's going to be 4 divided by 4. So in this case, it's a 1. So this is delta x1, then delta x1, etc. So that's going to be the base for each rectangle. Now, like I was just saying, you don't have to draw the whole thing. You can just draw the x-axis. So the x-axis is going to go from 0 to 4. The first interval is going to go from 0 to 1. And the last interval is going to go from 3 to 4. And the reason that we only need the first one and the last one is because of our friend right here's sum sequence. So you need to be able to tell it where to start, where to stop. And then this will be the delta x. So this is going to be using left endpoints. So it's going to actually start with this one. And then it's going to use the left endpoints until it gets to the 3. So for this one, it's going to be sum the sequence. And then for each rectangle, its height is determined by the function. So that's going to be 2x plus 1. And then its width, in this case, is just 1. It's delta x. Then you tell it the variable, tell it where to start, 0, where to stop, 3, and then the last step is delta x, which in this case is a 1. So when you do this for Riemann sums, it's always going to be the function times the delta x, comma, x, and then the start, the stop, and the delta x. And as you can see, the delta x is not hard to find, so that part is going to be straightforward. That part is straightforward. All we need to really worry about is where to start and where to stop. So in this case, 0 and 3. So go to second list, go over to math, get the sum. Go to second list, operations, get the sequence. And then this one is going to be 2x plus 1 times delta x. X is the variable, start at 0, end at 3, and go by steps of 1. So the step is the delta x. And then it puts it on the screen, and the estimate is 16. Now, when we're using the left endpoints for this particular picture, you use the left side, and so that leaves this little gap right here that it did not count. So 16 is actually an underestimate. The answer must be a little bit bigger than 16. Now we'll use the right endpoints. So we already did the formula for delta x, so that's still a 1. So that means that the interval starts at 0, goes to 1, and the last interval is from 3 to 4. And then use the right side of that, so it's going to start at 1. Use the right side of that, so it's going to stop at 4. So then it'll be the sum, sequence, then the height is 2x plus 1, the function, times delta x, and then x goes from 1 to 4, and the last part is delta x. So once you have this on the calculator, you can just either put second enter to get it back again, or you could just highlight it and hit enter, because all I need to change is this to a 1 and this to a 4. Everything else is the same. And now it says that it equals 24. Well, because we're using the right endpoint, that's like this rectangle right here, and it actually has a little bit extra right there, so the answer 24 is a little bit too big. Then for example number, or part C, use the midpoints. And the midpoint is usually the most accurate way to do it. So you once again have the interval going from 0 to 4. Delta x is still equal to a 1, which means the first interval is going to go from 0 to 1, the last interval from 3 to 4. But now use the midpoint. So what's in between a 0 and a 1? Right in the middle. You're right, that will be 1/2. And right here in between 3 and 4, that would be 3.5. So then we do the sum sequence. It's still going to be 2x plus 1 times delta x, with x going from 1/2 to 3.5, and then delta x. So that means it's going to go, because delta x is equal to a 1, that means it's going to go 0.5, 1.5, 2.5, and then 3.5. And plug all those in. And so this last one is going to be the most accurate. So now I need to erase the 1. So I think what I'll do is just erase the rest of that stuff and then put a 0.5 until 3.5 in increments of 1. And so 20. So the first answer was too small, 16. 24 was too big. And 20 is our best estimate. Now, how do we find the actual answer to see how good these estimates are? What you do is graph the original function, which is 2x plus 1. Then just go to Zoom Standard. There's the graph. And now go to Calculate. And number 7 will find the area. So the lower limit is 0. The upper limit is 4. And then it finds the area and says that the exact answer is 20. Then for example number 3. So then let's go with y equals sine x on the interval from 0 to pi. So from 0 to pi, sine looks like this. There's 0, here's pi. How much area is in this little part right here? Well, the biggest that it gets is 1. So if you estimate it with one big rectangle, just make a line straight across and make a rectangle, it would have a base of pi and a height of 1. So 1 times pi, that would be pi, 3.14. But of course it doesn't have this area, so it's got to be smaller than pi. Maybe it's 2 point something. So use midpoints of 10 rectangles. So what we really need is the x-axis. So the x-axis goes from 0 to pi, and now we need delta x. So for delta x, whatever the interval is, you subtract these two numbers. So that's going to be pi minus 0. And then it's divided by 10. So delta x is equal to pi over 10. That means that the first interval is going to go from 0 to pi over 10. Well, since it's going by tenths, then this is 1 whole pi, so right before that would be 9/10, or 9 pi over 10. Now use the midpoint. So what is right in the middle between 0 and pi over 10? Well, that means that you cut this in half, and if you multiply this by 1 over 2, that is going to be pi over 20. Then what about this midpoint? Well, there's a couple of ways you could do it. One is the gap between these two is a gap of pi over 20. So you could take pi minus pi over 20. That's one way. Another way is you average these two. So if you average a pi and 9 pi over 10, that would be right in the middle. I'm going to do it that way. Now, for the moment, I'm going to leave pi off. So this is 1 for 1 pi, and then this is 9/10. So then what's the average? So if you have a 1 plus a 9/10, and then you divide that by 2 and convert it to a fraction, that's going to be 19/20, so that's going to be 19 pi over 20. Now we can do the sum sequence. So it'll be sum the sequence, and then you put the function, that's the height, times the width, which is delta x, and then tell it x is going to go from pi over 20 to 19 pi over 20, and the last part needs to be delta x. So second list operations sequence. And then the function is sine of x, and then times pi over 10, with x going from pi over 20 to 19 pi over 20. And the step is delta x pi over 10. And then paste puts that on the home screen, and it says that the answer is 1.959. Well, let's see how close that is to the actual answer. So graph y equals sine of x. Have the window go from 0 to pi. Now, when I put 0 to pi, sometimes the calculator rounds that and it actually cuts off the last part of the pi. So what I'm going to do is widen this interval a little bit. Go from -1 to 4. Then that will definitely include 0 and pi. And for the y values, 0 to 1 is good enough. And then it draws the sine graph. And now, to find the actual answer, go to second calculate, number 7, starting at 0 and going to pi. And the actual answer is actually 2.0. So my estimate, when using just 10 rectangles, it's not too bad of an estimate. 1.959, if the actual answer is 2, that's pretty good.